Hi everybody. In this video, we are going to present the final form of the conservation equations and discuss the role of turbulence in the mixing process. For those of you who did not watch the entirety of the optional video posted on Reynolds averaging, I'm going to summarize the key steps and outcomes here so that you can still understand the final equations. In that video, we first defined the rate of change as a material derivative, which includes variations in both space and time. We then separated each of our variables into a mean component and a fluctuating component. So this instantaneous velocity here can be represented by two signals. The first is a mean signal that does not change at all in time and is constant. And the second signal is the fluctuations, which at each given instance represent how far away you are from the mean value. Lastly, we applied time averaging to the overall decomposed equations, and including applying a number of different averaging operator rules. The final derived result gave us the average conservation equations, and they look very similar to the instantaneous conservation equations that we started off with one key difference. And that is that this rate of change that we had previously not defined can be expressed in terms of two components. The first is how the mean quantity changes in time, and the second is something that captures the net effect of all of the turbulent fluctuations at that point. And this comes from what is known as an advection term, and it represents how the individual turbulent eddies are carrying different properties of the flow across our mixing plane. The final equations that we get after this derivation are shown here for the momentum, for the concentration, and for the heat. And what you can see from each of them is that they have all the same contributions in terms of a mean change in time on the far left, followed by a net effect of turbulent advection, and then source terms representing internal generation and losses, followed by the net effect of molecular diffusion and its fluxes. What we can do is move this advection term from the left side to the right side and group it together with the molecular diffusion. Both of these have derivatives in them. After moving the fluxes to the right-hand side of the equation and grouping it together, we now have this alternate version of the equation that has the mean change in time isolated on the left-hand side, and that is the result of a combination of both fluxes due to molecular action and what you might call fluxes due to turbulent or macroscale action. But in order for us to understand what these fluxes are, it's instructive to try and understand the phenomenology behind it. In order to do that, we're now looking at a sample time series of the vertical velocity fluctuations and concentration fluctuations that are taken at the same point in time. The statistic, this turbulent flux, is representing what is known in statistics as a covariance of two variables. If you are looking at this time signal and wanting to understand how it contributes to this covariance, you can identify specific types of events that are important. For instance, in this particular event here, you have a positive upward velocity and a negative concentration fluctuation. In terms of what's happening within the flow, this corresponds to the flow carrying a region of the fluid upwards across your plane at height z1, and the region of the fluid that it's carrying has a concentration that is lower than the mean concentration at that z1 mixing plane. So you're bringing lower concentrated fluid up across into the upper region. In the opposite sense, you can also identify regions that have a positive concentration fluctuation and a negative vertical velocity, meaning that the flow is carrying pockets of fluid downwards across this mixing plane, and these pockets of fluid have a higher concentration than the average value that's at the height of this mixing. And so this is representing the bulk action of large eddies directly carrying fluid both above your mixing plane and then down below your mixing plane. So if you consider a series of all of these types of events that I just identified, the covariance statistic provides the average result due to all of these individual events. Not every single event can be classified either in the manner on the left or the manner on the right. There are also other types of events that actually contribute to minimizing this flux. But on the average, these two types of events are dominating the statistic and dictating what the overall size and sign of the statistic are going to be. So the net result of the advection is going to be represented by this covariance, whose statistics are governed by the types of events that are carrying high concentration fluid down or low concentration fluid up. The advection is always going to have a sign such that quantities are moving in the net average from high regions to low regions on average. So it's much like the molecular flux is always going to be in the opposite direction of the gradient or be down gradient. As I mentioned, this is taking high concentration regions and moving them down to where it's lower, or taking it where it's lower and moving it up to where it's higher. However, one of the problems that we have is that these statistical covariances are very difficult to measure, and it would be helpful to have a simpler way to approximate them. One common assumption within the literature is to assume that these fluxes are proportional to the mean gradient in exactly the same way as you get the fluxes from molecular diffusion. So the definition for molecular fluxes is that the flux is equal to the negative of some diffusivity constant multiplied by a mean gradient. And the assumption is that the turbulent fluxes, these covariances, are also a negative of a turbulent diffusivity constant multiplied by the mean gradient. This type of assumption is referred to as either a gradient diffusion approximation or K theory. And I'm using the lettering K to indicate the diffusivity constant following the traditions of K theory. There are a lot of limitations and imperfect inaccuracies of this assumption, but for the purposes of learning in this particular unit, it can still be useful. In particular, what we can do is apply this gradient diffusivity to all of the variables that we have. So for the momentum flux by turbulence, the concentration flux by turbulence, and the heat flux by turbulence, where each of them have their own individual diffusivity constants. After we substitute for this gradient diffusion assumption, we get a final version of our equations where you can combine the diffusivity constants together into a leading term, and the derivative of a derivative becomes a second derivative. So you have a mean change in time, some sort of an internal source and sink term, and then a combined effect of the molecular and the turbulent fluxes. The same thing comes from the concentration. You get a combined effect of molecular and turbulent diffusivity, and the same for heat. You get a molecular and a turbulent contribution. The reason why this is useful and illustrative is because now we can provide a direct comparison between how fast molecular diffusion is versus the turbulent fluxes. And examples of the diffusivity constants are given here. We already learned about the diffusivity constants for molecular diffusion. They're on the order of 10 to the minus 6 to 10 to the minus 9, all of them with units of meters squared per second. The turbulent diffusivities also have units of meters squared per second. However, the values are significantly higher, on the order of 10 to the minus 3 to 10 to the minus 1. This is telling us that mixing due to these turbulent fluxes and turbulent fluctuations is faster than molecular diffusion mixing by orders of magnitude. And so you're going to start to see effects similar to what we witnessed earlier in the videos, where molecular diffusion is much slower than what happens when you apply a macro scale action such as turbulent fluctuations.